This is a continuation of my discussion on nucleotides. And I would like to say that this is the first recording I'm making after several months. So, the last one, which talked about the parts of the nucleotide, was actually in real life several months ago. And I finally have the time now, after doing some personal stuff, to resume these recordings, and I'm happy to be able to do this. So let's start. Maybe a little bit of refreshing ourselves on what we need to know about nucleotides. Like, for example, first remember that every nucleotide has three parts: a base, which could be a purine or a pyrimidine, a 5 carbon sugar, and phosphate. Notice here, since I'm not anymore going to talk about bases a lot, instead of drawing actual rings of pyrimidines or purines, I just, put them as letter B's here. We're not going to focus on these anymore. So now, what am I going to focus with? Well, here I think it's very important that we remember the locants for ribose. So in this case, this would be again 1 prime. This carbon here is 2 prime, 3 prime, 4 prime, and 5 prime. And well, you see that they color coded here 3 nucleotides, and allow me to just place the same locants on all of them. So that's the second set. This is the third set. All right. And here you will be seeing that we actually have them attached to one another. In the previous recording, I was very much focused on discussing a single nucleotide. But of course, you cannot have a nucleic acid without connecting the nucleotides together. Thus, I just decided that the first thing I'm going to show in this recording is the nucleotides already attached to one another. So how did that come to happen? So notice that, for example, this is the first nucleotide on top. The second one here is connected to the top portion by its phosphate, or via its phosphate. And it's like saying that the phosphate of the next nucleotide connects that thing as well as the previous nucleotide. Now, remember, the bond here between this 5 prime carbon and the phosphate, based on the previous recording, is called a phosphoester bond. Okay, which, again, when you say it's a phosphoester bond, it's a bond between the sugar right here and the phosphate. Now, in that sense, wouldn't that also mean that this bond right here is a phosphoester bond? Because, well, if you think about it, this is also a bond between the phosphate and the sugar. It's just that the other one, this one is connected to the sugar below, and this one is connected to the sugar above. But doesn't that mean that it's like saying that this phosphate right here has two phosphoester bonds that actually link the two nucleotides together? In that case, if you think of, like, connecting everything here, you could just say that you could unite these two, and if you do that, you can call all of these here as a phosphodiester bond. Sometimes they even call that a 5 prime 3 prime phosphodiester bond. Or sometimes they could call it a 3 prime 5 prime phosphodiester bond. But anyway, we call this basically as a phosphodiester bond, all of the things happening here. So it's safe to say that the bond that connects two nucleotides together is called a phosphodiester bond. And therefore, that's the same thing that connects the second and the third. So it's another phosphodiester bond. And then if you could just imagine here, I just cut it here, but you can just imagine it could continue again and again and again. And just to let you know, most of the time we have several thousand nucleotides building up RNA molecules. And then for DNA, it could go as much as several million, in fact. So nucleic acids tend to be very, very, very long molecules, much longer than proteins actually. Okay, and here, what we should know is that eventually this thing will stop at the very end. Probably after several thousand or million nucleotides below, it will somehow end, right? And so in that case, we have to pay attention to the names of the two ends in every nucleic acid strand. For example, at the upper part here, the defining feature here is the fact that I have here a phosphate that is free, meaning it's not, bound to anything. Normally, a phosphate is in the middle and is bound to something, but here you see the phosphate at the upper part, at the terminal part, bound to nothing. In that case, where you find a phosphate attached to a 5 prime that has nothing else attached to it as the 5 prime end. So this terminal right here is called the 5 prime end. Now, normally also you would notice that the 3 prime oxygen is always attached to something at the bottom, which is a phosphate. You will also notice that here the 3 prime carbon is also attached to phosphate. So it's like most of the time the 3 prime is attached to something. But I did say that if we ever find the end at the very bottom, you will find a 3 prime that is not attached to anything anymore. So what if what if this was the last nucleotide already, and then here there's nothing anymore below it. In that case, the defining feature of the other terminal or the other end is I have a 3 prime carbon with a free OH, nothing attached to it. Pretty much like the phosphate here, nothing attached in the opposite side. And in that case, since this is the special part at the other side, we can call this the 3 prime end, where there is an OH at 3 prime that is finally not bound to anything. Pretty much like how at the 5 prime end there is a phosphate that is finally not bound to anything else. Okay, so that means that in every nucleic acid strand, be it DNA or RNA, they would have the 5 prime end on one side, which is sometimes they call it like we imagine the 5 prime end as like the head portion if it was like a human being, and then the 3 prime portion is like the rare version or the backside of that thing, or probably the foot, okay, or the bottom or whatever, okay. And that analogy would make sense later when we talk about the central dogma. But now, as you can see here, we follow some kind of pattern. That, for example, if I start at the phosphate at the 5 prime end, of course, this is not attached to anything. This phosphate is, of course, attached to a 5 carbon sugar, and then that sugar is bearing with it a base at its 1 prime carbon. But then again, the sugar here is attached to the phosphate of the next nucleotide, which is attached to the sugar and then attached to the base again. And then you would notice that we could, make this go on and on and on. This will be repeating again several thousand or million times over until probably maybe I could just draw one last uh, let's say this is the last sugar here. um, we end at one point. So probably this is the 5 prime end and this is the 3 prime end. And this could be basically the backbone or the structure, simplified structure of any strand, that you will notice the phosphate and the sugar kind of conveniently attached to each other, forming a continuous chain. That's why sometimes they call it the sugar phosphate backbone, because it's basically, you know, where we find the continuous chain, okay, of components for a nucleic acid. So yeah, we can sometimes call this the backbone. And then protruding from the backbone are the bases, which again can either be purine or pyrimidine bases. Okay. Now, this would be pretty much the structure of a single-stranded nucleic acid, usually RNA. But sometimes we have two strands interacting with one another, as in most cases for DNA. So in that case, it's like I would have something uh, uh, like something that mirrors it. So phosphate, sugar, and then the base protrudes here. And then uh, let me just probably I I'm not really making this drawing too good, but It's actually not looking very good. But anyway, yeah, I think I'm starting to form some shape here. Yeah, let me just continue it until I match all of the bases at the other strand. Yeah, so this must be the last sugar and then the base. For a reason that I will tell later, if I do have two strands facing each other, the 5 prime end would actually be opposite, would be facing the 3 prime end from the other strand. And then the 3 prime from one strand will be facing the 5 prime from another. We call this arrangement as anti-parallel, and we will talk about it in another recording. But here, you would notice that if I have two strands, we actually see to it that their bases are kind of facing each other. And as I will teach in the next recording, these bases can actually be attracted to each other by hydrogen bonds, like so. Okay? And actually, maybe if I try to trace this sugar phosphate backbone, it may try to give you some hint on what I'm trying to draw here. If I try to zoom this out and then I just draw this backbone as a mere figure like this, and then this one also as a mere figure like this. And then what if I just try to draw all of these as just something like that? You will notice that we are actually trying to form some kind of ladder shape, which, well, apparently, if you try to imagine twisting this ladder, we would actually finally get to something which most of us usually draw as the structure of the DNA. So basically, this one, and I think a lot of us have the experience of drawing this as early as like high school. These things we are drawing are actually the sugar phosphate backbones. And these horizontal things here are the interactions between the bases of these two strands. And of course, this will be in more detail discussed when we go to the levels of organization as well as the properties of the DNA double helix.